Sören, good morning.
Yeah, hello, good morning.
Good to see you. I really enjoy seeing your face in a good mood here. And please share your screen.
Sure, yeah, I will start.
Meanwhile, I'll start very briefly presenting you because you do not really need any presentation. Just take a look at the name and surname, go to anywhere, and you'll see that this person has hundreds, no, dozens of thousands of citations, and he's quite an influential person in the community related to semantic technologies, scientific knowledge graphs, linked object data, and also starting recently with the neurosymbolic AI. So the talk that will be given by Professor Auer is about neurosymbolic AI with knowledge graphs and generative AI. Soren, the floor is yours, and I'm proud that you accepted. Thank you very much.
Yeah, thank you very much, Vadim. It's great and a big honor to be invited to give this talk. I'm very sad. I actually would have liked to also come in person to Lviv. Unfortunately, these days we have our retreat yearly L3S Research Center retreat, and unfortunately, I have some other responsibilities. That's why I was not able to come, but I hope it will be possible. And I'm really grateful and thankful about also the collaborations we have with you, but also other partners in Ukraine. We now have also some European Union funded or also German DAD funded projects with lots of universities in Ukraine. I think it's really great to foster this collaboration and maybe mitigate a little bit the results of this aggressive war. And from my side and I think I'm speaking also in the name of most of the people at TIB, and we are really supportive and hope that this difficult times will come to an end somewhere soon. And as long as it takes, at least from our side, we will try to do our best to yeah, support and work with you and collaborate. And so my talk is about neurosymbolic AI, and recently we have seen a big yeah, boost with generative AI approaches, language models. Knowledge graphs are around there already a bit longer. And some of the work I'm presenting is also done in the context of the German national research infrastructure. And there are some projects, for example, one for the engineering community, NFDI for ING, for the data science community, NFDI for data science, and for the energy systems analysis community with NFDI for energy. But before I start my talk, I want to briefly show you maybe the Leibniz University of Hanover, which you see there, the castle. It's the Welf Castle. And in front, you see the more modern building from the 80s is TIB, the TIB main building. And TIB was founded as a national library for science and technology. Actually, after the Sputnik shock in West Germany, I'm personally East German, but I also wasn't born at the time yet. So in 1959, Soviet Union launched this first Sputnik, and that was a bit a shock for the Western countries, how advanced apparently Soviet Union was, and that gave rise to the foundation of TIB as a national library for science and technology. And the idea was to make the literature and the scientific knowledge for science and technology accessible to researchers in West Germany. And now we are, of course, in United Germany, working not only for Germany, actually also in Europe and internationally. But that was a bit the foundation spark for TIB. And of course, we developed over the time. So we became part of Leibniz Association, and you already see a little bit, there is a lot of Leibniz. Actually, Leibniz University is not the only university having Leibniz in the name in Hanover. And our library is also not the only library in Hanover having Leibniz in the name. There is another library called Gottfried Wilhelm Leibniz Library. and the other university is Leibniz University of Applied Sciences. So there is a bit an inflationary use of Leibniz in Hanover, and in order to disambiguate that, I created a small knowledge graph already as an introduction. So you can see TIB. We are also the library of the university. This is one of our roles. So approximately 1/3 of our effort goes into being a university library, but 2/3 of our effort and budget we invest into being this national research infrastructure. And as that, we are part of Leibniz Association in Germany. We have 4 big research organizations. In addition to Leibniz, there's also Fraunhofer, Max Planck, and Helmholtz. So Leibniz is one of the 4 non-university research associations. But we, of course, are also closely affiliated with the university. And both have the namesake, Gottfried Wilhelm Leibniz. And to make the confusion perfect, he was actually born in Leipzig. But this is just an incident that there is a bit of proximity. The meaning is very different between Leipzig actually has a more Slavic origin, and Leibniz comes also from it, has a different origin. But he was born in Leipzig and he died in Hanover. He was also the librarian of the King of Hanover, but not very interested in being and writing the chronicles of the kingdom, but more in doing research and fighting with Newton at the time. And then, of course, from Hanover, there are also these Leibniz cookies. They are also named after Gottfried Wilhelm Leibniz. So 100 years ago, it became quite popular to name delights after famous people. Maybe you also have heard, know these Mozart chocolate balls, and what I've shown you here is a bit already disambiguating this space of different entities in Hanover being related to Leibniz, and that's actually already a small knowledge graph, where we have entities and relationships between these entities, and I will come back to this a bit later in the talk. But let me also start with some example about language models, and I want to illustrate a bit why we need this neurosymbolic AI with an example. So if you were asking ChatGPT a question about the scandal about Professor Auer, it came up with a long story of plagiarism, misappropriation of research funds, data manipulation, which was completely hallucinated. Nothing of this is true, but and I actually had to trick ChatGPT. I was also observing how they retrained or how the feedback was incorporated. In the beginning, I was just asking for a scandal around Professor Auer, and later I had to trick it already into describing the scandal here by telling ChatGPT that it's a journalist and it should write a summary about a widely publicized scandal. So I'm basically already telling that there is a scandal and it's widely known, and then it came up with the story. But they meanwhile trained also ChatGPT not to answer such questions. I could really observe from week to week how they basically the feedback was incorporated and questions, these hallucinations, basically the model was trained not to answer questions which would result into such hallucinations. I think if you ask this question now, it will actually do a web search and look for web pages about Sören Auer or scandal, and then say that it didn't find anything about it. And that already shows that the language model itself actually is not able to answer certain questions, but it needs more additional information. Like in the case of doing a web search, it's a bit this following this retrieval augmented generation paradigm, So how do these generative AI work? I think there's also this famous book of Daniel Kahneman, who also won the Nobel Prize for his research in cognition, psychology, And he devised that there are two ways of thinking fast and thinking slow. And I think what generative AI can do is thinking fast. Yeah, so based on statistical patterns in the data, in the training data, in millions of documents, it basically finds some kind of statistical correlations and quickly gives us an answer resembling what is there in the training data in a way. The other way is also thinking more slowly, basically, which means doing some reasoning, maybe doing some calculation, following some kind of trained reasoning calculation steps, maybe also using external tools and databases. And that's what language models or generative AI itself cannot do. But of course, we now try to incorporate that. And that's exactly also a bit what this neurosymbolic approach aims at, to combine generative AI with techniques so that in the result, we also can emulate this slow thinking and then solving more complex problems as well, reducing the number of hallucinations or confabulations, having more trustworthiness. So how does I would say that actually the language models, the machine learning, neural approaches pretty much resemble also what our human brain does. Yeah. So, um, and we both tend to hallucinate at times, or also humans believe in false information, fake news, yeah, make mistakes. So we have similar deficiencies, I would say, as the machine intelligence, but we have learned as a society to deal with these deficiencies of our brains. Well, we write things down in books, for example, which are peer-reviewed, where we have other people cross-checking, validating. We have articles, we have curated databases, we perform experiments to refute or validate our assumptions. We do simulations. So all these kind of things actually aim at a bit mitigating also the shortcomings of our neural brains. And I think we need to do the same for artificial intelligence. So, and the integration of these neural models with semantic knowledge representation, that's what's called neurosymbolic AI. And how are we aiming to realize that by putting a knowledge graph basically a bit in between? Yeah, so and even a more advanced version of a knowledge graph, I call this cognitive knowledge graph, where we have additional structures. I will show you some examples also about that in a minute. And the knowledge graph can basically moderate between the human and the machine intelligence. So what is a knowledge graph? So here you see on the right side an example of the DBpedia knowledge graph. So you see, as I've shown also in the very first slide, basically entities. Here we have Bob Dylan and Steve Jobs, and both lived in the United States. And Steve Jobs was a fan of Bob Dylan. And then we have attributes for Bob Dylan, like his gender, his birth date, his names, and so on and so forth. And we have these kind of relationships in the graph, yeah. And one of the first knowledge graphs, or probably the first out there, was DBpedia, which we extracted from Wikipedia. And this is actually an example from DBpedia. Meanwhile, there are many Wikidata, which is now integrated into Wikipedia. And what you see here on the left-hand side is actually not a knowledge graph, but it's a network of knowledge graphs. So each bubble on the left side is actually a knowledge graph in itself. Yeah, that's the linked open data cloud. There are billions of facts of such entity statements, entity relationship connections out there. And DBpedia is one in the middle, basically there in this linked open data cloud. And then you have different areas describing data sets in linguistics, for example, the green one, or the yellow one is government, open government data. We have a lot of life science, that's the red part here, life science data sets or knowledge graphs, which are openly published on the internet. But of course, there are also private knowledge graphs. And what is a knowledge graph? So it's a fabric of concept, class, property, relationships, entity descriptions. Also usually uses a formal knowledge representation formalism like RDF schema, Auer, which are W3C standards for that. And that distinguishes knowledge graphs, for example, from property graphs. Like Neo4j, for example, which is not a knowledge graph, but it's just a graph database. But you can build on top, of course, a knowledge graph, or you can use a triple store right away. But it requires this formal knowledge representation formalisms. And then in terms of information, knowledge, data in the knowledge graph, it covers often multiple domains, multiple sources, different levels of granularity, and includes, for example, also instance data, which can be open like DBpedia, Wikidata, private data, which, for example, is exchanged in supply chains, or really also closed data, which only one company has access to, like product models, for example. But it can also contain derived aggregated data, schema data like vocabularies, ontologies, metadata about provenance, versioning, documentation, licensing, taxonomies to categorize the knowledge, the entities, links between internal and external sources, and also mappings, for example. So these knowledge graphs are quite holistic in the sense that they contain the data, the ground truth as ground truth, but also metadata and vocabularies according to the same formalism. So I mentioned already that companies are building knowledge graphs. So this slide is actually 5 years old. Frank van Harmelen from Free University of Amsterdam was basically collecting the logos of companies here. And meanwhile, I guess almost all larger and medium-sized companies are also building knowledge graphs to organize the data. Especially larger companies often have a plethora of databases and knowledge or different IT systems, and knowledge graphs can help integrating and interlinking this, and that's what most of the organizations meanwhile are working on. So we want to integrate knowledge graphs with neurosymbolic AI, and for that also extend the concept of knowledge graphs, and in the end also establish a true human-machine collaboration. And I will cover this a bit in the talk today. Currently, we have these factual knowledge graphs, which describe real-world entities. The granularity is often atomic entities. Yeah, we have these entities and relationships. We can add and delete facts. But I think we need also to extend the concept of knowledge graphs, and we call this cognitive knowledge graphs, where we also cover conceptual entities, interlinked descriptions, which we call molecules or graphlets, concept drift, varying levels of aggregation, and emergent semantics. And basically, the idea is that as the base constituent of these cognitive knowledge graphs, we not just have entities, but also these kind of graphlets, so small patterns of knowledge which can reappear in different places in the graph, and which you can reuse, reusable patterns. And these can then also be used for reasoning, querying, graph completion, and so on. And maybe I illustrate that with an example. So if you look at a knowledge graph from precision medicine here, you see one about a patient who has a certain mutation, and then there is a treatment which the patient will undergo, and the treatment starts as a certain date, and it involves two drugs here, and a drug-drug interaction between those drugs is described in the knowledge graph. And then we also have a predicted outcome on the lower part, which is based on a claim made in a paper, in a scientific paper, and so on and so forth. And this is actually only a small example, a small excerpt. So the knowledge graph itself, of course, is much, much bigger. Yeah, you have much more information about the patient, also about the drug-drug interaction, and so on. So this is already very simplified, but it's already relatively difficult also for us humans to make sense of that if these knowledge graphs get very large and complicated. But what we also can see here is that certain of the entities are actually connected. Yeah, so we have several entities which describe the patient in the lower part here, lower left part. Yeah, and we have certain entities which describe the treatment, which involves the drug-drug interaction. Then is another pattern, and we have the predicted outcome. And these are patterns in the graph which describe certain things, but involve more than just one entity. Yes, typically a small network or pattern of different entities which are connected in a certain way. And as I said, we call these graphlets or also molecules, and they basically provide a structuring level between the entities and the larger knowledge graph itself. So, and of course, these patterns can also be reused. Yeah, so treatments similar have often a similar structure. Patients are similarly structured, so you can have many instantiations basically of these patterns in the knowledge graph. But we want to leverage them, for example, for querying, for also reasoning in the future, and many other things. So now, how can we combine language models with knowledge graphs? And if we look a bit what these are good at and compare them, so language models are very good at text processing, extraction, summarization, translation, generation of texts. But they have absolutely no concept of facts. Yeah, they still often and sometimes get factual information right, especially when it's already appears a lot in the training data. But if it's a bit more, yeah, not in the training data or not so frequent, then dealing with factual information is almost impossible with language models. Also, they are a black box, so they might contain hidden biases and are often also a bit superficial. Also computational expensive to train, to fine-tune and to query. Maybe the querying is not such a big problem. I would say it's maybe 100 times more expensive computationally than querying a knowledge graph or doing a web search. But meanwhile, computational resources got less and less expensive, so that this is maybe not such a big issue nowadays. Knowledge graphs, on the other hand, are very good at representing knowledge, integrating knowledge from different sources. They are human and machine readable, so we can scrutinize and validate things in the knowledge graph by looking at the entities and relationships. They are also quite transparent. We can add information about provenance and then can be traced where certain information came from. Yeah, and they scale relatively well in terms of querying, but require a lot of manual effort for integration and curation. So, and I think these two technologies have very different um, benefits and advantages and disadvantages. So combining them makes a lot of sense. Yeah. And in a way, unfortunately, knowledge graphs are out there already for almost 15 years. Um, and almost 20 years. I think the first dbpedia extraction I programmed in 2006, so that's 18 years ago. And I was actually hoping that within a few years they would gain really big popularity everywhere. This was a quite slow uptake. It's still not everywhere. I think there is a lot of potential. And one of the reasons is that there was this manual effort maybe required. You needed to know how RDF works and so on. Also, creating ontologies or mappings is quite complicated. And that's actually what language models can help us. They can help creating the knowledge in the knowledge graph by suggesting things and recommending. You can create mappings and queries for the knowledge graph using language models, for example. And language models can become something like a front end for human interaction with the knowledge graph. While the knowledge graph can represent a base of validated, trustworthy knowledge, organize, integrate knowledge from various sources, and then, of course, also provide input for enterprise and domain-specific training and fine-tuning of language models. So, and I created here a little bit a pathway of from my perspective, we can proceed to more artificial general intelligence. So the step with the language models, using language models in isolation was the beginning in a way, but lacks this factual knowledge. Meanwhile, we use relatively widely this retrieval augmented generation approach, where we add additional basically information documents during inference or query time. The next step, what we also work on, is knowledge augmented generation, so that the language model actually has access to structured information sources such as databases, knowledge graphs. Then a next step, I would say, is agentic generation, where the language model or the generative AI basically also learns how to use external tools such as reasoner, APIs, computational services. And when we add then also self-reflection, goal setting, and other things, we might come to artificial general intelligence later on. So, and now I was talking a bit about the general vision and maybe general ideas, and now I would like to show you a very concrete example how we develop such a neurosymbolic knowledge graph or neurosymbolic AI system based on a large knowledge graph. And we developed that in science for scientific research information. And I want to start comparing a bit how we deal with scientific information to other domains. And here are some examples of how information and knowledge was exchanged 20, 30 years ago. So we had, for example, in Germany, extremely popular were these mail order catalogs, which you see on the left-hand side. This is actually one of the last issues of the Quelle catalog with Claudia Schiffer. These mail order catalogs were a huge business, of retail companies, basically. I would say I'm East German, so it was maybe also one of the reasons why the Iron Wall between East and West was falling, because East Germans wanted to have access to all these cool products described in these mail order catalogs at the time, And then you have street maps, maybe some of you remember the time 15, 20 years ago, you had to buy a street map if you wanted to go from A to B, and every year there were new maps being published. There was a whole industry of maps, And I think no one of you would use nowadays a PDF scan of a street map if you can use something like a navigation system, right? Or Google Maps, for example, phone books, encyclopedias. So these are just some examples how some of these information flows in the digital area were completely disrupted and replaced by digital services, by navigation systems, digital maps, by Wikipedia for encyclopedias, by platforms like Amazon, eBay, or Idealo for e-commerce. And these are not just pseudo-digitized copies of the analog artifact. So it's not just a PDF scan of a mail order catalog or a PDF scan of a map or an encyclopedia, but it's really a digital-born service which allows to zoom into the data, which has a lot of dynamics, where the business models also completely changed. There's much more focus on interlinking of data services and search in the data. We have a lot of integration of crowdsourcing and data curation there. Sometimes people even don't notice, but they contribute to the data in these platforms. If you use Google Maps, for example, already by having it switched on, you already contribute to the popularity or frequency measurements in Google Maps for points of interest and so on and so forth. Yeah. And what about now scholarly communication or research information in science? And this is actually an area which is quite important worldwide. So we spend globally 1.7 trillion on research and development. So this is not million, not billion, but trillion. And I would say that a large share of this money is not efficiently used because often we cannot really make use of the scientific knowledge. Yeah, and that's illustrated here on that slide. Basically, in the 17th century, in the time of Leibniz, Gottfried Wilhelm Leibniz, yeah, there was the first scientific journal published, the Philosophical Transactions of the Royal Physical Society. And even at the digital age, it hasn't changed much. The typography maybe is better now. And of course, we can access, we don't have to print and distribute the physical copies. We can just download those articles. But it's, I would say, only a pseudo-digitized version of the analog artifacts. And we publish millions of papers every year. Actually, in science and technology alone, it's, I think, 3 million articles every year. And we don't really build a knowledge base, but we build rather a pile of papers. Yeah. And I would say that the scientific method, in a way, is at stake. Yeah, so we drown in this flood of publications. Many of the publications also are not cited. We have a reproducibility crisis. The quality of peer review deteriorates. And even though we now work a lot also on research data management, often the methods do not scale, are not automatized sufficiently, like user integration, explainability, security, and so on. And it's a bit the danger that we end up with a research data swamp instead of a nice data lake. So challenges we are facing are also reproducibility crisis. I mentioned these already. And the root cause of problems is that often we have information hidden in the text, yeah. So these unstructured textual content is not really well machine readable. We can hardly integrate results from different papers, from different approaches together. That makes also it very difficult for AI. Imagine you could not build a navigation system by just scanning all the maps out there, yeah, and scanning them to PDF. You would not be able to build a navigation system, or you could not build an e-commerce platform by scanning mail order catalogs, right? So you need from the ground novel or well represented knowledge and database, and for that. Also identifiability, we can meanwhile identify documents and also in addition to the documents, also authors, for example, with ORCIDs, with DOIs, but we actually want to identify the research approaches, the methods, the data sets, the techniques, the approaches, the evaluations, and so on and so forth. Yeah, and that prevents us from collaborating better. We have a bit this one brain barrier in science, and often scientists look for the needle in the haystack. So I think you all know this. If you search on Google Scholar for something, you find thousands of results. Yeah, if you look for the famous genome editing method CRISPR, you find 250,000 results. It's actually also a screenshot I made in 2019. So 5 years ago, meanwhile, I think it's 1 million results you find for CRISPR. And if you're then interested in specific questions like how good is the quality with regard to precision, safety, cost, what specifics has it when you do genome editing with insects, or who has applied it to butterflies. You're completely lost in this pile of information. So how can we fix it? And there was this famous librarian, Vannevar Bush, who shortly after World War II in the US wrote this influential article, As We May Think, where he foresees a possible future in which machines will start thinking. Yeah, it took quite long, but I think we are now actually at the um, yeah, at the verge of this area where machines are thinking. And Vannevar Bush at the time coined this concept of memex, like a memory extender, a magic desk who would provide you all the information at your fingertips, what you need. And I would say it was a bit esoteric at the time. But nowadays, it actually becomes really possible, and we have many of the building blocks at hand. And that's what we now want to apply for research, basically building a knowledge graph for research. So for the concepts, overarching concepts like research problems, definitions, research approaches, methods, for the different artifacts where in addition to publications, we have data, software, audio, video, and then of course also domain-specific concepts like definitions, theorems, proof, methods, and mathematics, experiments, data, models in physics, substances, structures, reactions in chemistry, and so on and so forth, and give each of these entities an identity in the knowledge graph and establish basically the links and the relationships between them. And this is called the Open Research Knowledge Graph. And maybe here, instead of showing you the slides, I can show you actually a live demo of the Open Research Knowledge Graph. I hope you all can still hear me well and follow the slides well. So let me open here a new browser window. Can you see the browser?
Yes, we can see the browser and we do hear you quite well.
Perfect. That's great. So, and I start with something which we developed just recently. It's called ORKG Ask, and you can all try it out. I can actually send you also the link here on the chat. It's available at ask, like asking questions, .orkg.org. ORKG, like Open Research Knowledge Graph. And here you can ask any question you like, any research question, and we try to find an answer in 76 million scholarly documents, which we have indexed in a semantic database with abstracts. And we have some example questions here. For example, how do social networks influence political polarization and echo chambers? Really important topic, unfortunately, also in Germany. We just recently had elections in some East German states, and these populist and parties unfortunately gained a bit more traction. Once you ask the question, basically, what do? We look for the most relevant papers in the 76 million ones. And these are the papers which are listed here below. Yeah, so you see here we have the top 5 most important papers retrieved there from the 76 million using vector database. And then we ingest the information from these papers, not everything, not the complete full text, but the abstract, the title, and sometimes also introduction and conclusions. Basically, we add this to a language model and then ask the language model. And in that case, we use an open source one. We use Mistral, so everything runs on our TIB infrastructure and our own data center, so we are not dependent on commercial services here. And then the language model creates the answer based on these documents. So we are not asking the language model in the beginning but we basically first retrieve the documents and then only given the specific information, and that's exactly the research and augmented generation approach. Only with this specific information, the language model helps us summarizing, synthesizing, and integrating information from these different papers. And that's what we see here. So we have as answer, the use of social media has been identified as a significant factor. Yeah, so these platforms include Reddit, Twitter, and others. Research examining the impact is essential. So echo chambers are established based on users' beliefs and actions, and so on. So basically here it's summarized, and we can then also see where the information comes from. Of course, since this is generated by the language model, there might still be some hallucinations. That's why we show here also this warning on top, yeah, that you have to check it very carefully. But you can basically here click on the reference. You will then jump to the corresponding entry in our reference list below. And there you can then look at the articles. So we extract some further information from the articles, like the answer, the insights, a TLDR summary, conclusions, results, methods. And you can also regenerate the content. So here, then the language model is queried again. Let's see if we get, now we get also some result for the first one. And you can actually then also click on the respective publication. Oh, sorry. Yeah, and then you basically get in the abstract here, also if you have the full text, you will get a link to the full text, and you can read basically the complete paper again. Here we have the links, yeah, so you can then open the paper and validate and verify this information. And then we also show some related papers down here to this one. You can also, of course, filter. On the left-hand side, you see here filters. For example, you can filter by year. You can filter by different languages. You can also filter by topic, by impact, by citation count, by keywords which need to appear in the title, in the abstract, or by publisher, for example, by authors. Yeah, so there, for example, maybe one thing which makes sense is to filter by citation count, and we could say greater than, let's say, 10. And if we add the filter, then basically the answer is regenerated. And you see now it already runs a bit longer because the answer is now not cached anymore, but regenerated. Maybe now it's actually the first answer I would say was maybe a bit superficial. And here, my impression is it gets a bit more specific, maybe because we now have filtered already the papers to those who apparently received some attention and were considered also valuable by other researchers. Yeah, and you can also extract some information specifically. So you have here added columns. So what could we add here? I don't know, type of networks. For example, I could add, I don't know if it makes sense here for this. It's more a sociological question. So I can move that to the top. And then you see that this type of networks now appears here as a second column. And it extracts then this kind of information from these articles. And here shows us Twitter, for example, or election campaigns, what they investigated in these particular papers, yeah, the type of social networks. Sometimes it makes sense, sometimes a bit less sense. Maybe, for example, the first one here, maybe is not exactly what I had in mind, but maybe my question here didn't make much sense. So, but this only to show you that you can, with these edit columns, you can actually then create custom extractions and filter the content, or extract information in a more domain-specific manner. So you can also save these questions, you can share them, you can download them in LaTeX or CSV. Yeah, so if you want to integrate some of this into your paper, you get here the LaTeX and the BibTeX code for download. There's also a feature recently added as top authors. So then it actually retrieves not only the top 5, but the top 100 articles and queries, looks for the authors basically in these publications, and then shows us a ranked list of the authors. So this is something, if you look, for example, for peer reviewers, you could use this feature, or for evaluators for research proposals. And of course, this takes a little bit more time because we have to retrieve here not only the 5 top publications, but a larger number. And then it sorts us basically ranks the list of authors based on the number of publications they were involved in. So here you see the authors, their affiliation, and the number of papers they have in this top 100 list. And you can then also directly go to the ORCID and look at their ORCID profiles, for example. Good, so this is the ask feature, but our idea is, of course, that this is just the first step. So once you have asked the question and got such a already initially structured result here, our idea is that you then also maybe check, validate it. You can then download it as a CSV, and you can then integrate it into the Open Research Knowledge Graph. And this is here more like a search and answer, question answer engine. But in the end, we actually want that these answers are stored, refined, revised, and stored in the ORKG. And I want to show you how this works. Also, if you go to the classic ORKG, you have here different domains you can choose. For example, let's choose engineering, and in the engineering domain, we have also subfields. And then below, we have not papers, but we call these comparisons of the state of the art. Basically, overviews of the works contributing to a certain research question. And here, for example, we have a comparison of approaches on Germany's energy supply. So this is a big topic for us, because we want to improve or we want to transition to renewable energy till 2050. And there were a lot of studies, actually 25 studies here, which we added to the Open Research Knowledge Graph. And this is work we have done in the course of the NFDI for energy systems research, and NFDI for engineering, in order to basically organize these contributions here. So each of these 25 publications is like 20, 30 pages long. So if you would print them out, you would have 500, 600 pages of paper. But if you're interested now as a politician, for example, how much renewable energy generation, like wind power or solar systems, do we have to install in the next 20 years? Then it's really difficult to answer this question, and you need to do research in this area, and we want to make it easier to answer such questions. So we added these studies basically to the knowledge graph here. So we have the energy sources which are covered by the studies. We have the scenarios they assume. So the first study here, for example, 100% CO2 reduction till 2050. The second one, only 95% reduction. And since it's here added in a machine readable way, it looks a bit like a spreadsheet, like an Excel table, but it actually is the knowledge graph. You can see here the entities, the IDs, the identifiers that pass to these entities. Yeah, so it's a highly structured knowledge graph. And then this allows us to also create visualizations. Yeah, and here, for example, we have the installed capacity of renewable energy, which would be required to manage this transition. And you basically see that most of the studies think with like 400 gigawatt, it could be sufficient. Some assume it's much less, other think we need much more, but you can basically get a quick overview of the gist of the information from these different studies here. Yeah, so and how do these comparisons end up in the Open Research Knowledge Graph? So we envision that ask, what I've shown you before, is the first step, that you start with a question, and then you do some custom extractions, and then you basically start with the preliminary organization. But of course, we also need some manual contribution. So that doesn't work fully in a fully automated manner currently. So, and I want to show you basically once you click on one of these studies here, so it's basically a paper, an article, we will get information about this particular study. So you also have the metadata here, authors, where it's published. You can also access the paper online. We have a discussion forum. Um, you can also view the graph basically here. So it shows you also then the graph, and you can explore the graph there. But I have to say, I don't find the graph is a nice gimmick, but for, I don't know, for navigation, maybe not so useful. But here you can then also edit basically the knowledge graph. So once you're logged in and you click the edit button, you basically have the possibility to edit all values here, or add also additional ones. You can also click these light bulb things, and that's also then shows you smart suggestions, and they actually come from a language model. So we feed the summary of the paper into a language model, and then the language model suggests properties which could be added here. So, but I now add one property manually. For example, I type something, and while I'm typing, it already suggests me existing properties and shows me the documentation also, which are defined already in the ORKG. So I can choose them, and the same way it also works with values. So for example, I can add here Hanover, and then I get suggestions not only from the ORKG itself, but also from geonames, from Wikidata. For example, here I could choose the Wikidata resource of Hanover, and then I get actually information via this external ID. So if I click on it, it basically retrieves me all the information from Hanover. So I have a lot of information then, including geocoordinates, who the mayor is, and lots of more information, which I don't have to add manually. And that shows a bit what the benefits of these open knowledge graphs on the web of data are, if we can connect these different knowledge graphs with each other. Yeah. So maybe I go back to the contribution description and I delete this triple, because of course here in that case doesn't make sense. Yeah. So I removed it again and I stop editing. And on the right-hand side here, you can also see the provenance, who has added what there, and you can follow the timeline of the edits over time. Yeah, so it works a bit like Wikipedia, Wikidata. One more thing I wanted to show you in this comparison. Once you have created such a comparison, you actually can publish these comparisons as well. So we generate DOIs, and they are also then formal publications. You see here the authors, and you see that we also assigned a DOI to this comparison because, of course, it involves some manual effort and research to add this. And once then it's published, then you also can add it to your publication list, for example. And there are many more features, like you can export as LaTeX, CSV, RDF, Jupyter Notebook. You can launch a Jupyter Notebook and then create visualizations with the data right away. Yeah, and many other features we have here in the ORKG. Good. So maybe this as a showcase of a neurosymbolic system, and what we have seen here is really the integration of machine intelligence, of knowledge graphs, and then of course also of the humans via crowdsourcing. And let me maybe jump back to the presentation, but I can now skip most of the part because I've shown you this. Maybe just one bit information about this ORKG Ask, how this works. So there we have a semantic search system, we have the paper corpus, we have language model and knowledge graphs. And it's also, of course, a bit inspired or similar like typeset.io elicit. And I wanted to show you also the technical implementation. So here is a bit how it works technically. So we have these 76 million articles indexed in the vector database. So we generated embeddings using the nomic embedding model. We have it in the vector database. We retrieve the top relevant documents, top 5 by default, but you can also load more. And then we use 2 prompts, one to extract information from the individual documents and another one to synthesize the answer, basically based on all the top 5 or 10 retrieved documents. So that's what the LLM then does here, generate the answer or extract information. And here are the two prompts also. So we basically explain the language model, what needs to be done, show with an example what results we want to have. Yeah, and then the model basically generates these results. As I said, in our case, we currently use Mistral, and not even the largest one, but the 7 billion Mistral model already suffices for these tasks. Yeah, and then of course our idea is also to integrate the human in the loop. I've shown you already some examples. So the idea is sometimes to have the machine in the loop and sometimes the human in the loop in order to build and augment and enrich the knowledge graph. And there we also have developed a lot of techniques. Usually in the ORKG, you see them with this bluish color, basically where you can launch the generative AI in the background to give you some suggestions, for example, to suggest a research problem or suggest certain properties to be added, which I've shown you also. Or we can also annotate abstracts of papers automatically. And of course, the work I've presented here is something where many people are involved. So we have different also groups here: Jennifer Sousa, Markus Stocker, Lars Vogt, several postdocs. We have a team focusing on community management. So if you would be interested in maybe organizing some of the research, maybe one more thing I could quickly show you what we also have. These are observatories. So if you go to the ORKG, we have these observatories. So these are areas in the Open Research Knowledge Graph for specific domains here. So for example, here we work with people about invasion biology. And then there is an observatory where we list the organizations and the members, and then specifically the content related to this particular domain. So if you're, for example, interested in building an observatory for your domain of research, you can get in touch with the guys from our community management team. Then we have a lot of PhD students, which you see here. Also Vlad, for example, is from Ukraine. And we have a software development team. Here, some of our former PhD students like Yasser and Allard are now working as postdocs in the software and service development. So they were also, Allard and Yasser, developing this Ask system. Um, yeah, and a few more people there. And this is really a service which we not only develop within a project, but we have actually many projects, but it's also part of the strategic TIB to further develop the Open Research Knowledge Graph service in the next years, or as long as it provides value to researchers. So we have also some base funding specifically for sustaining and maintaining this service. Good. So maybe just one quick mentioning of Ascensa. This is a spin-off company which I founded 10 years ago. So they actually built a neuro-symbolic AI platform for enterprises. I will not talk much about it, but if you are interested, you can go to ascensa.com or ascensa.my. You can even try it out yourself. And some of my former PhD students are working there, and they build a very comprehensive stack of knowledge graph, semantic technology components, implementing all W3C standards and many other cool features, which is specifically tailored for enterprise. Because I was talking a lot now about how we can apply this in research, but there are also, of course, many enterprise applications. Yeah, and that concludes my talk. Thank you for your attention. So summarizing, I would say we need to reinvent scholarly communication. I think knowledge graphs are perfectly suited, and also this neurosymbolic approach for organizing research information in science and technology and also other domains, to make also humans and machines collaborate better. I don't think it will be possible to do everything just by machines, and we should also be in the steering seat and hold the steering wheel, of course, in this AI developments. With our Open Research Knowledge Graph, yeah, we work on creating a knowledge base for science to represent scientific knowledge. And we need this synergistic combination of human, expert, machine, symbolic, and semantic intelligence. That's what we are working on strategically. Yeah, so thank you very much for your attention, and I think we should have also a few minutes for questions and discussion. Thank you very much.
Thank you very much, Sören. That was an enlightening talk. Thanks for that. Do we have questions here in the audience? Yes, please.
Hello, thank you very much for your presentation and for your project. I have a small question about what the most complicated technical problem you solved when you worked on this project. I mean technical problems, yes, some complicated problems, so you have solved. Yes.
Yeah, thanks for the question. So there are actually many complicated problems. So like the most challenging is maybe really the knowledge extraction from the scientific literature. Yeah, so extracting information, so extracting some high level, like the topics which are discussed in the paper. That's relatively easy. Maybe also the research question which is addressed by a paper. But extracting, for example, we work, and especially also our Ukrainian PhD student Vlad Nechaskin works on this topic, extracting task dataset metric values from scientific literature. So if you look at, for example, machine learning research or computer science in general, often there are papers which solve a certain task. They use a certain benchmark data set for showing the advantage over the state of the art. And then they report certain values they achieved according to this benchmark for their algorithms. Yeah. And figuring out what task they try to solve and what benchmark data set they use, that's relatively easy. There we reach, or relatively easy, we reach 80–90% precision recall. But to identify what values their algorithms, the performance basically, that's extremely complicated, and there the precision recall drops to, I don't know, 20–30%, because the representation in the papers is very different. Sometimes it's in tables, sometimes it's somewhere in the text. They use different units, slightly different definitions for reporting the metrics and things like that. So this is a really challenging problem, and this is just one problem. Only for this domain of algorithmic research, for example. If you go to material science and other sciences, there are many more similarly challenging problems, and this knowledge extraction is something really, really difficult. And of course, we also work on avoiding that, so that in the future, hopefully, papers are generated right away in a way that we don't have to reverse engineer and extract information, but that the information is represented right away in such a way that it can be used semantically. For example, Dr. Markus Stocker, group leader at TRB, he works on the reborn approach. So there the idea is, while you do research, you already organize the contributions, the results in such a way that they can easily semantically represented in the knowledge graph. And then we don't need this reverse engineering. But since all these millions of papers are out there, and still every year millions are produced in this traditional way, we of course also work on this knowledge extraction from the legacy literature, I would call it. And that's extremely challenging and hard and quite hard, and of course also then involving maybe the users since it cannot be solved in a fully automated fashion, you need to involve the users, and getting this right is something we work on and continue to work on.
Okay, thank you very much. More questions? Yes, please. Alex.
Hello. So I don't work in this field, so I have a very naive question. So you described a very large number of publications and a difficulty in extracting information. Would you be willing to comment on a low-tech solution to this problem, namely discouraging overpublishing and cutting down on the number of predatory journals?
Exactly. That's what we also do at TRB. Yeah. And of course, there is also a change by funders and so on, that it's not about quantity, but more about quality. You're perfectly right. That's what we need. Yeah, less quantity, more quality. But even with if we have, instead of 3 million publications, only 2 million, or even only 1 million or 500,000, it still is quite a lot. So I think this will not suffice. And I think also the number of publications still increases, because maybe not because in the Western countries people publish more, but there are countries like India, like also South America, Asian countries, which now also invest more in research. So there are basically also a lot of new people and publishing and aiming for publications. So that's also something I fully agree we need to work on. But I think just with that, we will not solve the problem, yeah, because I think we need to organize also the knowledge in a better way.
Yeah, fully supported. Let's kill ACM, IEEE, string nature, and the like, and let us have ORPG instead of that. Thank you. More questions? Yep, Roman.
Thank you for the great talk. So my question would be, how interconnected are the knowledge graphs and the large language models? So is it like the information from the knowledge graph goes into a neural network, and the output from the neural network goes back into the knowledge graph, or are they more strongly interconnected? Or so because you said you also wanted to combine these two, so my question would be, how strongly are they interconnected then?
Yeah, so that's what we also work on. There are many different techniques. Like what we now implemented in Ask, for example, is a bit like a retrieval augmented generation approach, right? So we retrieve certain information where we don't use a language model, but we still use embeddings to retrieve the relevant information. So that's a base technology, which is also then also used in the language model. So via the embeddings, we retrieve the most relevant documents, doing a similarity search in this vector space, basically in the vector database. And that's and then we ingest some of this retrieved information into the prompt, inject it into the prompt and then get something back. We also work on fine-tuning. That's another way to fine-tune the language model for specific tasks. So, for example, for extracting certain, this task dataset metric value example I gave you. So this is a good example where we can maybe fine-tune the language model by giving it a lot of examples of existing information. We have, I think, thousands of these already existing, also manually curated task dataset metric value contribution descriptions. And then with the full text of the paper and these structured extractions, basically fine-tune the model to perform better on this task, to find the values in new literature better. So this is another approach. Then we work on this knowledge augmented generation. It's maybe a bit related to the slide I've shown in this vision, right? So that we also integrate, I can actually also open it again briefly. So, no, that was, and of course I can share the slides later on with you, so you can also look it up. So that was this slide here, yeah. So retrieval augmented generation is maybe the shallowest integration, and then we now want to, of course, also integrate the knowledge graph better to give the language model access to more structured information. And then the next step is also using external tools, reasoners, APIs, computation services. Yeah, so that's maybe a bit the approach of a deeper integration of language models, generative AI, and not only knowledge graphs, but generally other sources. But for example, also I think even in this agentic generation, the knowledge graph can play an important role because they can describe the APIs, the computation services, so that can help the language model to access these agents and additional computational resources.
Thank you. Yet more questions? Okay, I have a couple. What do you think about using foundational or upper-level ontologies as knowledge representation patterns for knowledge graph auto-completions? What do you think about knowledge reuse in the context you presented?
Yeah, like we reuse knowledge. I've shown you this example. When you search for a property, for example, in the Open Research Knowledge Graph, we suggest properties which are already defined, and actually not only properties in our Open Research Knowledge Graph, but we also want to integrate other ontologies, and upper level ontologies could be also used there. but in particular also domain ontologies in the different sciences, in life sciences, in engineering. There are many ontologies out there. So that's what we also are actively work on to improve this. Fully agree, and I think it's very, very important. But on the other hand, when we have this kind of crowdsourcing approach, I think it's also not realistic that the knowledge will always be 100% correctly represented. Yeah, so we will have some mistakes and flaws and errors and duplications. So we don't want to prevent this because that would increase the usage barrier so high that already now, when we make it relatively simple, it's quite difficult or we work hard on making it easier and easier so that people can contribute easily. And the effect is that they will also make mistakes, and we don't completely prevent that right now. We want to make it easy to fix these mistakes later on also, but not completely prevent it. That's why also the knowledge base, the open research knowledge graph, will not be a consistent knowledge base in the sense of description logic, that you have a consistent T box and A box there where you can reason on. That will probably not be the case due to this crowdsourcing and also automatic extraction, which always has some flaws and errors. So there will be always also some certain percentage of problematic information in there. We just want to make it easier to identify those and fix it. And then maybe on certain subsets, you can, of course, also do some reasoning, but maybe not on the...
We've lost you. You muted.
Sorry. No, I just said in the end, reasoning on smaller subsets, which you then manually like define and create, can be possible, but not on the whole knowledge graph as a whole.
Yeah, true. So you immediately lead me to my second question by saying that consistency is very hard to be ensured on the whole, this big knowledge graph. So what are the consequences for semantic querying of those leaves on the graphs and some reasoning? So you can reason on these small consistent islands within a knowledge graph, or it is still possible to auto-validate the knowledge graph, and that might be a way to repair it in terms of making it a bit better reasonable.
Sure, yeah. That's of course also what we work on, but since it's constantly every day there are people adding something, I'm not sure it will be possible to make it consistent. We saw that also a bit with Wikidata, Wikipedia, or if you look at schema.org or OpenStreetMaps, these are other examples. I think they will never be really fully consistent from a reasoning and logic point of view, but still they provide amazing value. Yeah, so you can query them in certain parts, you can do reasoning, and you can use them for question answering and for data integration. So I think they're enormously valuable, even without this formal logical reasoning.
Okay. Nothing is perfect. I fully agree with you. So thank you very much for a very nice and very valuable talk. I look forward to welcoming you once here in Lviv at our nice campus. So we'll work on that, I believe. So
yeah, thank you very much. We'll love to come over at some point. Thank you.
This closes our keynote session, and now you guys may feel free to take lunch at Tau Trapezno, which, as Professor Spivakovsky said once, it looks like at Glasgow Caledonian University. So the quality is appropriate. Please go ahead. And we return back to the first session of the main conference in approximately an hour from now. Thank you very much for coming.